Assalamualaikum and a very good evening to Professor Dr. Wong Shavun. Our group will present to you about the Mechanical Vibration Group Project Assignment 3. Our group consists of 4 people, which is Munira, Umar Dari, Abdul Rahman, and myself, Muhammad Hidayat. Okay, let's go to the introduction. Okay, for the introduction, what is mean by vibration itself? First, vibration is a mechanical phenomenon whereby oscillation occur at an equilibrium point. The oscillation may be periodic, such as the motion of the pendulum, or random, such as the movement of a tire on a gravel road. Vibration can be desirable, for example, the motion of a tuning fork or the cone of a loudspeaker. However, vibration is also an undesirable, which is wasting energy, creating unwanted sound. For example, the vibrational motion of engine or any mechanical device in operation. Satu part. Next. On the other hand, vibration isolation is a process of isolating an object, such as a piece of equipment, from the sources of the vibration. Vibration propagates via mechanical wave, and certain mechanical linkage conduct vibration more efficiently than others. Okay, there are two types, which are passive vibration isolation and active vibration isolation. For the passive, it makes use of materials and mechanical linkage that absorb and damp this mechanical wave. Active vibration isolation involves sensors and actuators that produce destructive interference that cancel out incoming vibration. That's all for introduction. Next.
Next, the problem statement. Mechanical machines must be placed correctly in order to reduce vibration transmission to the surrounding space. Instead of the roof or the wall, the optimal spot to install a vibrating machine in a building is on the ground level. However, this is not always practicable, and the isolation system must be constructed to minimize transmission. Furthermore, it is critical to choose machine types that cause less vibration, such as centrifugal versus reciprocating ones. The high expense of a centrifugal compressor is the fundamental reason why reciprocating machines are still preferred. Figure beside depicts a 9,200 kg reciprocating air conditioning machine compressor placed on a roof. The compressor emits different compressor rotational frequencies, primarily at 60 and 120 Hz, to a room directly below the compressor. A vibration study can be performed by using the source pulse receiver model. Spring and damping components and inertia blocks can be used to reduce transmitted vibration from a vibrating machine. Figure beside depicts a machine bolted to a rigid floor. The force transmitted to the floor equals to the force produced by the machine. There are various more methods for reducing the transmitted force due to vibration. Next part is the solution. Solutions on various ways of minimizing the transmitted vibration. In many practical circumstances, the dynamic force that creates vibrations can be reduced but not eliminated. Vibrations can be controlled using a variety of approaches. First, controlling the system's natural frequencies and avoiding resonance under external excitations. Second, introducing a damping or energy dissipating mechanism into the system to prevent excessive response even at resonance. Third, using vibration isolators to reduce the transmission of excitation force from one part of the machine to another. Lastly, reducing the response of the system by the addition of an auxiliary mass neutralizer or vibration absorber. For the possible solution for the vibration problem, the best approach to a vibration issue is to eliminate it in the first place. Intelligent design is significantly less expensive than developing a faulty design and then trying to repair it afterwards. For the source, the vibration can be reduced by replacing the machine with a higher quality or other type of machines that is quieter, adjusting the unit's operating speed to eliminate structural resonance, and last, include a tuned vibration absorber and employ active vibration control. For the path, isolators, springs, and inertia blocks are commonly used to reduce vibration. The primary principle is to keep the natural frequency of the machine on its base as low as possible in relation to the excitation frequency. For the receiver, vibration can be minimized by adding structural damping and modifying the system's natural frequency to prevent coinciding with excitation frequencies. This can be performed by adding stiffness, which raises the natural frequency, or by increasing mass, which decreases the natural frequency.
Now, let me present to you about the 3 different ways of isolating the vibration. Okay, first is support on isolation spring mounts. Heavy-duty isolators are utilized in building system and industry, such as mechanical spring and spring dampers, because most industrial machinery is designed with reciprocating or revolving elements which cause vibration. Spring mounts are a crucial piece of isolating equipment employed in the gear. The unbalance of the machine's moving part typically the cause of the vibration. Any piece of equipment can have its lifespan shortened by the vibration and instability. These factors can also cause high-frequency noise by transferring vibration to nearby structures. Secondly, we can use the machine attached to the inertial mesh. Okay, the machine is mounted on an inertial mesh and supported by mounts. The addition of the inertial mesh creates a compound spring system if the floor is flexible. Problem should not arise if the natural frequency on the floor is higher than the destructive frequency of the machine. Inertial mesh are usually made of concrete with reinforced bars. Inertial mesh also usually used due to their increased stability of the system, lower center of gravity, giving more weight distribution and minimizing the effect of external force that could be used. Okay, last but not least, we can use roof-mounted vibration isolators. Okay, roof-mounted equipment including air handlers, fan and condenser require special handling to prevent noise and vibration from entering the building. To solve the problem, structural tubular support systems are available for mounting rooftop mechanical equipment. Typically, the vibration isolation is provided by custom-built unit that incorporate both the roof curb and spring isolation into one complete structure. For mounting rooftop mechanical equipment, there are robust structural tubular steel support solution available to address the issue. Usually, specially constructed system that combine the roof curb and spring isolation into a single unit are used to offer vibration isolation. Okay, next part.
Hello, and my name is Umar Hadari bin Zahiri, and my matrix number is 200520. So for my part, I will explain about how I will describe about the equation of motion of a single degree of freedom. So firstly, the free body diagram of the element should be drawn. Given single degree of freedom, the mass, the stiffness of the spring, and also the viscous damping should be labeled like this image. Like this image, the force is going downwards, and then the spring and the damper is drawn. And then the forces should be labeled in the y direction to get the following image. The mass of the element goes downwards, while the force of the spring and the dampers goes to the opposite direction. So the force is the mass of the element. It will go downwards, and then the force that will oppose the mass is the spring of the force of the spring, and also the damping force. Okay, so next. Right, then according to the Newton's second law, which is the force is equal to the mass times acceleration. In this case, it is F equal to mx double dot. The summation of the forces in the y direction is equal to mx double dot. So therefore, the formula of the force of the spring is kx, and formula of the force of the damping is dx x dot, and also the formula of the force is mx double dot. So by this equaling the summation of the forces in the Newton's second law, we could get mx double dot equal to the force minus the force of the spring minus the force of the damping. And then we could obtain from there, we change the forces into the x into the x and x dot, we will get mx double dot equal to f minus kx minus dx dot, and then the final equation of motion that we can get is the mx double dot plus dx dot plus kx equal to ft, which is the final equation of motion. So m is the mass of the system, the k is the stiffness, d is the viscous damping, and the ft is the excitation force. So that's all for my part.
Assalamu alaikum wa rahmatullahi wa barakatuh. My name is Abdurrahman Majid Sinan, and my matric number is 201418. This is the party of the group project. So calculate all the fundamental vibration parameters and transmissibility of the machine using 60 and 120 hertz for the 9200 kilogram chiller. So for this question, we got some variables here. So we're going to use the 60 hertz and the 120 hertz individually. Means like we're going to calculate twice using each one of these. Also for the damping ratios, for the steel, we're going to use two different values, and for the rubber, we're going to use two different values. First of all, we try to find the natural frequency WN using this law right here. But since we don't have the K and we're trying to find the K as well, we're going to use the constant gravity for it. So after we calculate it, we get 11.0736 radian per second. Sorry. Okay, for the next page here, the second step is using the same equation, but this time we're going to replace the K, put the K back in, and which is going to be equal to almost, it's 1,128,000 Newton per meter. This one is going to use later in the next transmissibility formula. We're gonna, as I mentioned before, we're gonna use the 60 hertz and 120 hertz individually, and we're gonna use the 4 damping ratios we got right here. We're gonna use this equation to solve everything. We're just gonna put all the numbers that we got. These are the results we got for the rubber and steel at 60 hertz, and for each damping ratio, these are the four solutions we got for the 60 hertz, and these are the other 4 solutions. So in total we got 8. So this will be for the calculation part. Thank you very much for listening.
So to conclude, so in an industrial environment, there are several sources of vibration, which include impact operations, rotational or reciprocating machinery, transportation vehicles, and many others. Vibration frequently causes excessive bearing wear, crack formation, faster loosening, structural and mechanical failures. Mechanical failures. Some methods for reducing vibration include adding vibration isolators, an inertia block, a huge mass directly attached to the machine, or adding a seismic mass and suspension. So that's all from us. Thank you.